It was a stunning evening. Two moons hung low near the horizon, slender crimson crescents, their faint light shimmering on the sea. The sun, a red disk that dominated the sky for weeks on end, had finally slipped behind the jagged northern hills. The peak summer heat had faded, the evenings were no longer a humid swamp, and the sky now blazed with the light of 50,000 stars. All the familiar constellations were there, along with hundreds more known only to the most dedicated astronomers. Suddenly, one of the stars began to brighten. Observers watched with delight as it grew and grew in intensity. This was no cause for alarm. Generations earlier, they had learned this was a cosmic explosion, the triggered death of a nearby massive star. Despite their advanced knowledge, they still preferred the traditional name for these events, a guest star. The guest star quickly outshone all others in the sky, becoming brighter than the dozen planets in their system. Soon, it was brighter than the dual full moon. Spontaneous celebrations broke out across the globe. Guest stars were common, happening about once a year, but this one was sure to be historic. Yet, as most people celebrated, one observer watched with concern. Their job was to monitor wind patterns in the upper atmosphere. Several satellites provided real-time data, and the measurements showed a dramatic drop in ozone levels, perfectly aligned with the guest star's increasing brightness. If this continued, it seemed their protective ozone layer would be gone in less than a week. Though just a story, there is no doubt that if a guest star, a supernova, appeared so close, it would mean the end of any civilization. In this case, on one of the first worlds to emerge in the cosmos, less than 1 billion years after the Big Bang, supernovas would have regularly dotted the already crowded night sky. The early universe was an active, fertile, and violent place. Galaxies were still forming then, bursting with round after round of intense star formation. While those explosions enriched the interstellar medium with the heavy elements needed to build rocky planets and possibly life itself, they also posed a tremendous risk to any life emerging on those worlds. So when did those worlds first appear, and what were they like? How can we know what variety of planets exist out there, both today and in the distant ancient cosmos? This journey to the first planets will take us through an uncountable variety of wondrous worlds, from great blue Jupiters with atmospheres of raining glass to tiny frozen rocks teetering on the abyss, and may even give us hints about the mystery of alien life in the universe. The Europa Clipper space probe launched on October 14th and will use gravitational assists from Mars and Earth to reach arguably Jupiter's most interesting moon in 2030. Of course, if those gravitational assists are misjudged, even slightly, the probe could spiral off into oblivion. Precision is hugely important when exploring the universe. There very well may be an alien civilization right around the galactic corner, or at least the beginnings of one. It might be on a planet not unlike our own, a water-rich world orbiting a yellow-white star. It might be something far different, like a parched moon of a gas giant hugging the limits of habitability around a red dwarf. But it is unlikely the signs of life will be obvious. Otherwise, we would have seen them by now. Instead, they will be subtle, mere shifts in the spectrum of light, something only a super telescope of the next generation will be capable of detecting. So Courtney Dressing knows she has to get this right. A professor at the University of California, Berkeley, She was tapped by NASA to co-lead the initial development stages of its next flagship mission. A telescope so ambitious it will make the James Webb seem modest. Currently named the Habitable Worlds Observatory, the telescope itself will not be launched for decades. According to Dressing, if it were imagined as a 100-meter race to launch, we would be putting on our shoes. But the Habitable Worlds Observatory will not just be a planet-hunting telescope. It will be humanity's first serious attempt to search for life itself, and will do so with an unfolding mirror several times larger than Webb's. With that kind of resolving power, it will take actual images of dozens of nearby Earth-like exoplanets, and will have the power needed to search for biosignatures, traces of elements hinting at the presence of life, in their atmospheres. While current telescopes like the James Webb can perform similar observations, they are limited to only giant planets. This new supertelescope will instead target Earth-like worlds, small rocky planets. It is the future of space telescopes. And so, how far we have come in a mere 30 years. For centuries, astronomers assumed strange alien planets orbited other stars. It is not a huge leap in logic. Our sun is nothing special, neither extremely small nor extremely large, so there should be nothing special about the appearance of planets in our own solar system. Thus, any average star should probably have planets. But what kind of planets? And how many? Does every star, of which there are hundreds of billions in the Milky Way galaxy alone, have a planetary system? And if it does that system look like ours? Just how typical are we, with a quartet of rocky planets and a quartet of giants? Is Jupiter the largest possible planet, and Mercury the smallest? Yet as astronomy advanced into the late 20th century, the vast majority of astronomers believed hunting for other worlds was a fool's errand. According to Princeton astronomer Josh Wynne, exoplanet hunters in the 1980s and 90s worked in an atmosphere of skepticism bordering on hostility. The main issue was finding them. Planets may seem large to us. Our own Earth is so vast its curvature is barely perceptible, but they are nothing compared to stars. Our own sun could swallow the entire Earth over 1,000,000 times and still have room for more. The largest planet in the solar system, Jupiter, weighs less than 1,000th the mass of the sun. Indeed, if you were an astronomer viewing the solar system from 10 parsecs away, Jupiter and the sun would appear roughly half an arcsecond apart. That is about the same visible diameter as a small coin sitting several kilometers away. And size is not the only difficulty when hunting for planets. If an object is luminous enough, it can still make itself visible to astronomers. Take neutron stars, for example. They are no bigger than a typical city, yet they blaze so intensely they can be seen from millions of light years away. But planets have no advantages here either. The sun is roughly 250 million times brighter than Jupiter. So when the first confirmed exoplanet was discovered in 1992, it was not by any traditional astronomical technique, and the planet did not orbit any traditional kind of astronomical object. Two astronomers, the Canadian Dale Frail and the Polish Aleksander Wolszczan, announced an unexpected discovery: two planets orbiting a pulsar. Not a nearby star, not a mid-sized star, not any of the usual suspects. One of the strangest objects in the universe. A pulsar is a kind of neutron star that blasts beams of radiation into space as it rotates. They are arguably some of the most extreme objects in the universe, second only to black holes. At only a few kilometers across, they are relatively tiny, yet due to their crushing gravity, the tallest mountains on their surfaces are only a few millimeters high, and if you fell from one, you would reach half the speed of light before hitting the ground. The fastest pulsar spins at tens of thousands of revolutions per minute, and the pulses they release contain photons with energies 10 trillion times stronger than visible light, flooding their surroundings with deadly radiation. Yet PSRB 1257 plus 12, sitting over 2,300 light-years from Earth in the direction of the Virgo constellation, seemed to have a planetary system. Frail and Wolszczan found evidence for them not by studying the system directly. It was much too far away. Instead, they used subtle variations in the pulsing signal from their host star. Planets do not have much mass compared to their parent star, but it is not zero. Whispers of gravity can be felt from even the weakest sources. As planets orbit their parent stars, they gently tug at them, causing the star to wobble ever so slightly. This causes, among other things, a Doppler shift in the light coming from the star. The physics behind this is the same as the familiar rising and lowering pitch of a passing ambulance. When the star moves toward us, light gets squeezed to shorter wavelengths and higher frequencies, while the opposite happens when the star moves away. Pulsars make exceptionally delicate instruments for measuring Doppler shifts because their pulses are incredibly regular, flashing away in our sky with a regularity, cadence, and perfection of rhythm that compete with our own atomic clocks. As for Frail and Wolszczan, after accounting for the motion of Earth and Sun, the delay in timings due to the pulsar's radio emissions traveling through the interstellar medium, and the occasional glitch where the pulsar suddenly switches frequencies, they found a Doppler shift that could only be explained by two orbiting objects, each with a mass roughly 4 times that of Earth. After a naming competition held by the International Astronomical Union in 2015, humanity's first 2 known exoplanets are now known as Poltergeist and Phobetor, a beast-like character from Ovid that appears in dreams. They are joined in this strange system by their sibling Draugr, named for undead creatures from Norse mythology, discovered in 1994, which is currently the smallest known exoplanet, less than twice the mass of our moon, a testament to how sensitive pulsars can be as exoplanet detectors. The names are fitting. Pulsars are undead stars, the leftover cores of once bright living suns that still emit leftover radiation. So it was not until 1995 that astronomers found their first exoplanet orbiting a sun-like star, and that discovery required much more precision, determination, and outright luck. Working with his research advisor and future Nobel co-laureate Mitchell Mayer, Didier Queloz found the first hints of a reliable signal in the shift of radiation coming from 51 Pegasi, an unremarkable sun-like star about 50 light-years away. But the data implied something truly bizarre. The signal suggested the planet was massive, roughly the same mass as Jupiter, but orbiting far too close to its star. Just a mere 0.05 astronomical units, 1/8 the distance Mercury orbits from the Sun. It would take years to convince the astronomical community of the observation's validity, a condition Queloz regarded as requiring a soft insanity to persevere through. Take, for example, the planet HD 189733b, a gas giant 10% heavier than Jupiter, roughly 65 light-years away. Unlike the orange and yellow hues familiar to Jupiter, this exoplanet has a deep cobalt blue atmosphere, and that atmosphere is deadly. An umbrella would not help you here. It rains glass sideways, with winds up to 7 times the speed of sound. Or take TRES 2b, the darkest known exoplanet. Sitting roughly 750 light-years from Earth, this exoplanet is exceptionally dark. Initial estimates suggest it reflects less than 1% of all light hitting its surface. Despite its vast size, larger than Jupiter, whatever its atmosphere is made of, it absorbs almost all visible light. A close-up approach of TRES 2b would seem like landing on the surface of a black hole. Then there is J1407b, the super Saturn located 450 light-years away. A gas giant, this exoplanet hosts a ring system that would put Saturns to shame. Orbiting J1470b are over 30 individual ring systems, each millions of kilometers across. Combined, the rings span a diameter of 180 million kilometers and contain an entire Earth's mass of material, making it over 600 times larger than Saturn's. The rings utterly dwarf the planet itself. Picture in your mind the wildest planet imaginable, with whatever fanciful composition and orbit you can dream of. Chances are this planet exists, and many more besides. But when discovering new exoplanets, alongside the Doppler shift method, more properly known as the radial velocity technique, the most powerful scheme is called the transit method, involving nothing more than staring at a star for a long time and waiting. Planet hunting with the transit method involves searching the heavens for tiny eclipses. If a star hosts a planet, and the plane of its orbit happens to line up with our point of view, then occasionally the planet will cross in front of the star's face, temporarily blocking a small amount of light. This effect is minuscule and relies on pure luck, but if you stare at enough stars for long enough, you will eventually detect the telltale sign of a planetary transit event. In 2009, NASA's Kepler Space Telescope became the world's premier planet hunter. The telescope continuously observed roughly 500,000 stars in the direction of the constellation Cygnus, searching for signs of slight dimming. That mission alone produced a treasure trove of nearly 3,000 confirmed exoplanets and thousands more candidates. Even one of the very first planets found by Kepler was full of wonders, something ripped straight from science fiction. Kepler 16b is a gas giant with a mass between Saturn and Jupiter, sitting 245 light-years away. What made it surprising was not the planet itself, but the system. Kepler 16b does not orbit one star but two, the first ever confirmed circumbinary planet. Sitting on the planet's surface, you could watch as its twin suns dipped below the horizon, recreating the iconic Star Wars scene, minus the sand. But despite the success of the transit method, astronomers need a variety of tools to paint as complete a portrait as possible for every exoplanet, especially in the hunt for the very first in the universe. The transit method is by far the easiest known method to find exoplanets, but it only gives a measure of a planet's radius based on the dip in the star's light. Astronomers must use other methods to estimate the planet's mass. From there, they turn to complex modeling to make reasonable guesses about a planet's composition and structure. For example, we generally know the abundance of elements in the universe and how they interact. If a planet is roughly the same size and mass as Earth, it is unlikely to be made of light elements like hydrogen and helium, and more likely made of carbon, silicon, and water. Kepler's successor, the Transiting Exoplanet Survey Satellite, or TESS for short, uses a variety of methods packaged in one spacecraft to measure as many properties as possible. At present, after 6 years since the mission's launch, TESS has identified 7,138 candidate exoplanets, with 440 confirmed by follow-up ground-based studies. In 2024, TESS discovered TIC 365102760b, a planet sitting 1,800 light-years from Earth. The discoverers nicknamed it Phoenix, for good reason. This planet is so close to its parent star that it should be nothing but a roasted cinder, especially after its star entered its red giant phase. But somehow this world has retained its atmosphere, an incredible and so far unexplainable feat. Astronomers suspect this act of planetary resistance will not last long, and the world will lose its grip on its atmosphere in less than 100 million years. The next great planet hunter will be the Nancy Grace Roman Space Telescope, currently scheduled to launch in May of 2027. Its unique properties will allow it to create a census of up to 1 million exoplanets in the Milky Way galaxy. But perhaps the most important method of revealing an exoplanet is studying its light directly. During a transit event, most light reaching our telescopes comes directly from the parent star, but some light is either reflected off the planet or passes through its atmosphere. This contamination of the light is incredibly small, but if we capture a strong enough signal during the transit, we can isolate the contributions from the planet and measure at least some of the elements present. Webb has shown us that not all exoplanets are grim wastelands. There are also those showing hopeful signs of life, like K2-18b, a planet only 120 light-years from Earth, first studied in detail with the new telescope in 2023. This world is a sub-Neptune, and a spectrum of its abundant atmosphere shows faint signatures of methane and carbon dioxide. These elements are possible in a lifeless atmosphere, but also in a life-filled one. So our hunt for alien worlds is still in its infancy. Yet even with only a few thousand confirmed detections, we have deduced the existence of worlds we could not possibly have imagined. The universe is bewildering in complexity and dizzying in scope, and exoplanets are no exception. As we attempt to plunge deep into the past to discover the first exoplanets, we must next confront the amazing variety that could exist. The planet is being torn apart before our very eyes. Its parent, however, is fairly normal, a K-type star slightly smaller and cooler than the Sun, sitting about 66 light-years away. But it hosts a small family of planets in a peculiar series of orbits. A gas giant with a very tight 56-day orbit, roughly 2/3 Mercury's distance from the Sun, and a second planet roughly Uranus's mass, sitting even closer with just a 14-day orbit. In 2024, a team of astronomers led by Stephen Kane at the University of California, Riverside, announced the tentative discovery of yet another body. This was no gas giant but a terrestrial world 30% wider than Earth, clinging to its star in a brutal 2.2-day orbit. Of course, no life likely exists on this planet. No atmosphere, no water. This world is scorched by its proximity to its star. But that is not the only source of its horrors. The dance of the gas giants in their incredibly close orbits means they exert enormous tidal forces on the Earth-like planet, stretching and squeezing it like putty. The tidal forces are easy enough to calculate. Just a simple application of Newton's laws. And it is also easy to calculate how much energy is transferred from the orbits of the giant siblings into tidal deformations of the small terrestrial world. The conclusion is startling. The constant stretching and squeezing, pulled here and there by the gravitational forces of the giants, releases so much energy the world itself is glowing, caught in a perfect tidal storm. With an estimated surface temperature of 2,600 Kelvin, this Earth-like planet is lit up like an incandescent light bulb. This is no mere speculation or flight of science fiction. It is a sound scientific estimation based on a surprisingly small amount of information. Just one example of how clever research can reveal the wonders and majesty of worlds millions of light years away. In almost all cases for these thousands of known alien planets, all we truly know is a thin slice of data, represented by a line on a plot. But astronomers are enormously clever and used to making great leaps of insight based on meager scraps, because that line is a spectrum. The concept of atomic spectra was developed in the mid-1800s, before we even understood the nature of atoms and subatomic particles. Indeed, explaining atomic spectra was one primary motivation for developing quantum mechanics. Each element on the periodic table emits light at a combination of very specific wavelengths, and each molecule does the same. When astronomers look at a distant exoplanet as it transits its parent star, some starlight filters through the planet's atmosphere, and the elements and molecules leave their individual fingerprints in the spectrum. From there, astronomers turn to modeling to build their understanding of these foreign worlds. We understand how physics and chemistry work. We know how atmospheres react to different intensities of light wavelengths. We know how gravity affects a planet's ability to retain an atmosphere. We know how molecules mix and dance in an atmosphere. It does require some guesswork, and statements about exoplanets are always up for revision. But through these techniques, astronomers have deduced an astounding variety and complexity of planets within the galaxy. Perhaps the greatest surprise was that we could detect exoplanets so easily in the 1990s. That is because the first known exoplanets were completely unlike anything we knew from our solar system. Yet hot Jupiters are not just our first known exoplanets. They are among the most common. Astronomers now believe hot Jupiters start in distant orbits, but through gravitational interactions and planetary reshuffling, migrate inward to closer orbits, where they spend the rest of their days roasting alive. Some experience such intense radiation they become bloated and distended, with tidal forces turning them egg-shaped. While hot Jupiters are fascinating, they are unlikely homes for life, at least the kind we know, which arises on small, rocky planets in their star's habitable zones. Exoplanet surveys have found many such worlds, especially around small red dwarf stars, because those are easier to find with current techniques. While we have yet to confirm liquid water on any extrasolar planet, we have many candidates deserving follow-up investigation with the Habitable Worlds Observatory. But we just do not know how many exoplanets exist in the Milky Way. At bare minimum, We suspect there is, on average, one planet per star, meaning a few 100 million planets call our galaxy home. But many estimates suggest planets are much more common, depending on how easily they form, including rough estimates on rogue planets, exoplanets without a parent star drifting through interstellar space. There may be up to billions of worlds in our galaxy alone. Those guesses suggest that if we are searching for life and want to hunt for it on Earth-sized planets orbiting sun-like stars within their habitable zones, we may have up to 5 billion planets to search. 5 billion chances for life. Our Earth, as unique and special as it is, may have billions of siblings. And Earth is far from alone. With even the beginnings of these searches, astronomers have discovered an astounding variety of exoplanets, each completely foreign to our solar system, smashing past generations' expectations. Besides hot Jupiters and their too close orbits, there are circumbinary planets, worlds orbiting two stars at once. There are even double planets, objects of roughly equal mass orbiting a common center. If Pluto qualified as a planet, it would likely be a double planet due to its relationship with Charon. There are rogue planets wandering interstellar wastes and Trojan planets following a larger sibling. There are super-Earths and mini-Neptunes, worlds of every conceivable size, larger than Jupiter and smaller than Mercury. There are worlds covered in ice, lava, thick hydrogen layers. There are dry, airless worlds and ocean-covered water planets. There are planets without cores and planets with almost no crust. There are worlds made of abundant carbon, silicon, or iron. Decades of searches have unearthed thousands of worlds, representing only a tiny sliver of those in the Milky Way. But even with that meager sample, we continually find ourselves surprised. It seems galaxies are enormously efficient at producing planets, and this efficiency may allow them to construct planets as early as possible in their histories, perhaps in the universe's history. Unfortunately, we do not fully understand planet formation, as it unfolds over hundreds of millions of years. But besides fully formed exoplanets, we also have thousands of detailed observations of young stars, protoplanetary disks, and more. We can stitch these images together to form an overall story and attempt to predict how early planets could have formed in the young universe. Planetary systems like our own begin as diffuse clouds of hydrogen, helium, and a smattering of heavier elements. These clouds dot every galaxy, containing enough material to fashion thousands of stars. When these clouds collapse to form a system, most material coalesces toward the center, where friction heats it to high temperatures, becoming a protostar, a star not yet igniting fusion. The material eventually forms a flat plane around the protostar, the beginnings of a protoplanetary disk. The vast majority of the disk is hydrogen and helium, but sprinkled throughout are dust, microscopic grains of heavier, more complex molecules. Just like dust clinging to surfaces in your home, dust in a protoplanetary disk sticks together, finding each other in the spinning sea of lighter gases. Dust clumps together molecule by molecule. Over hundreds of thousands of years, these clumps become large enough, roughly 100 meters, to completely change the disk's fate. At roughly this size, the clumps, now called planetesimals, have their own gravitational pull, which they use to inflate their size by attracting new material within the inner regions near the young star, which has begun fusing hydrogen. the heat is too much for light elements like hydrogen and helium to remain, and too much for volatile elements like water and carbon dioxide to remain as solid ices. Only heavier elements like iron, carbon, and silicon, and their combinations can survive. The inner regions become home to terrestrial worlds, some barren lumps of rock, others clinging to thin atmospheres, while outer regions form larger, gaseous worlds. This process, repeating generation after generation, star after star, across nearly countless billions, fills every galaxy with a population of planets. So with this picture, heavy elements seem a prerequisite for building planets. And even though planets are numerous, they are small. Earth or Jupiter or any exoplanet may seem enormous on human scales, but they represent mere rounding errors in cosmic accounting. Once there is even a small amount of raw material, the universe's simple physics will give rise to a planet. But how long did it take the cosmos to generate enough raw material? Planets do not fare well facing a dying star. The small, rocky world precariously close to the guest star, as it went supernova, was no exception. First came the flood of gamma-ray radiation, stripping away the ozone layer that, for billions of years, had protected life from harmful UV radiation. Oceans overheated, and plants and algae could not withstand the radiation, tearing apart the food web's heart. Then came high-energy particles known as cosmic rays, ripping through the planet's magnetic field, showering the surface with deadly energies. Cancer spread like a global pandemic across all species. Then, centuries later, civilization long crippled, came the final blow. A shockwave, weakened as it expanded from the initial explosion but still powerful enough to tear the atmosphere away like dandelion seeds in the wind. Had the supernova been any closer, even the mantle and inner core might have evaporated. As it was, the planet they once called home was dead, a barren husk of rock, its once verdant lands and abundant oceans now dust on a frozen breeze. The young universe was not friendly to life. Billions of years ago, the cosmos was much smaller. Galaxies were closer together and collided more frequently. Stars formed intensely. Some galaxies produced stars thousands of times more often than the Milky Way does today. As those stars formed, they also died in magnificent and frequent supernova explosions, irradiating their vicinity and posing serious hazards to any life finding a foothold in this hostile era. Thankfully, planets are exceptionally easy to make. The first stars were made entirely of hydrogen, helium, and trace lithium, the only elements fashioned in the Big Bang's fires. They fused heavier elements in their cores and even more through explosive deaths, seeding young galaxies with ingredients needed to build planets. We do not yet know when this process began, but we know it did not take long. Consider the star TOI 561. TOI 561 is a sun-like star roughly 280 light-years away. At first glance, it is unremarkable. 79% the sun's mass and 85% its radius. To your eyes, it would look like any other star, slightly orange. But TOI 561 is not just old. It is ancient. It is over twice our sun's age, having formed roughly 10.5 billion years ago, right when the Milky Way was first emerging. When TOI 561 formed, the Milky Way was not as enriched with heavier elements, so astronomers classify it as metal poor. TOI 561 is one of the oldest stars in our galaxy. And in January 2021, a team led by Lauren Weiss at the University of Hawaii announced an unexpected discovery. It has a family of planets. This was confirmed by independent analysis by Gaia Lace-Deli of the University of Padua. It was no fluke. One planet orbiting this ancient star is a super-Earth, twice Earth's mass on a breakneck 10-hour orbit. Besides its extreme orbit's mysteries, the mere existence of this world opens a confusing question. How did a rocky planet, composed of heavier elements, form around a star with barely any? This question lingers with no clear resolution. For decades, astronomers assumed stars and planets go hand in hand. When a star has higher abundances of heavier elements, it should fashion more and larger rocky worlds. But the cosmos seems to have its own designs. Despite its age, TOI 561 grew a healthy planetary system with enough material for rocky, Earth-like planets. The planet orbiting this ancient star is likely not a viable home for life, roasting in its parent star's ferocious heat due to extreme proximity. But if super-Earths could form around TOI 56110.5 billion years ago, it is not a great stretch to argue regular Earths could have formed around the same time. Life first appeared on Earth almost as soon as the surface cooled and oceans and continents arose. It seems once our planet could support life, it did. Perhaps some world, among trillions yet to be mapped, observed, or discovered, around a stellar cousin of TOI 561, had the right combination of elements, temperatures, and conditions for life. Life in the early universe would have been challenging. The cosmos was more active and volatile billions of years ago, resulting in higher star formation and stellar death rates, soaking every galaxy in more high-energy radiation. Planets may have quickly formed around most stars, and any life emerging would have had to navigate the ultimate catastrophe, their own sun's supernova explosion. Simulations suggest planets do not fare well facing such energies. At best, dense nickel and iron cores remain, with everything else evaporated. Yet nature gives another surprising twist. Just like hot Jupiter's apparent impossibility, planets should not exist around pulsars, leftover cores of giant stars surviving supernovae. Another idea is planets form around pulsars from supernova material itself. After blasting off at a fraction of light speed, much material cools and coalesces around the neutron star, introducing fresh planet formation. These ideas highlight how easy planet formation is. It can even happen around a dead star. So we can guess rocky planet formation happened extremely early, perhaps within the first billion years of cosmic history, as soon as enough stellar generations enriched interstellar gas clouds with heavy elements. As for life, while we cannot say for certain, it had a chance on these young worlds. Despite chaos raging through violent emerging galaxies, planets almost certainly formed that were suitable. Many attempts at life were likely snuffed out by energetic explosions or gravitational destabilization. But the universe made planets abundantly, and it is very likely somewhere, billions of years ago, when first stars and galaxies began filling the cosmos with light, some creature called a primordial world home. But so far, we have only considered rocky worlds, terrestrial planets like Earth, fashioned from heavier elements with liquid water oceans. Life may be far stranger, and so might the planets life calls home. If we extend our definition of planet, we might push back even further into time. Arikoth remembers. On January 1st, 2019, humanity got its first close-up view of a world that had known only darkness. The object, Arikoth, a word from the extinct Powhatan language of the eastern United States, meaning sky or cloud, sits in the Kuiper Belt, a distant ring of scattered, frozen leftovers from our system's formation. It is small, gray, and dirty. Two misshapen lumps of ice and dust roughly 36 kilometers long and 15 to 20 kilometers on a side, glued together by a gentle bump billions of years ago. The object has only been visited once, in a flyby lasting minutes by NASA's New Horizons spacecraft, launched in 2009. We only know one face of Arikoth because the flyby did not last long enough for a full view, and the probe was traveling too fast with too little fuel to orbit. But this little object holds a story of miracles. Arikoth is incredibly ancient. It was present when our solar system's protoplanetary disk first coalesced, escaping to the fringes during the chaotic era of first planetesimals. It watched as new planets emerged from the swirling maelstrom, crashing, colliding, forming anew. Some ejected into interstellar wastes. As survivors, 4 rocky inner planets, 2 gas giants and 2 ice giants, rearranged into stable orbits. Arikoth waited billions of years, knowing only the dim, distant sun and its feeble gravitational grip, 1 foot in the solar system, the other toward stars beyond. Then a little spacecraft, no bigger than a piano, sped by, its first visitor since formation. Before Arikoth could register New Horizons' presence, through radar signals or gravitational deflections, it was gone. Unperturbed, Arikoth resumed its watchful sentry at the solar system's gates. Arikoth represents not just a lonely outpost. It is a tiny clump of dust and ice, far smaller than any planet, barely noticeable cosmically. But it is much easier for the universe to make small debris like Arikoth than massive planets like Earth, let alone giants like Jupiter. Objects like Arikoth are more likely to survive catastrophes befalling their system, like a giant planet's death or a sun's implosion. So how early could something like Arikoth form? Kuiper Belt objects are made of relatively simple, common elements like hydrogen, carbon, silicon, and oxygen. Hydrogen was abundant within the Big Bang's first minutes. Carbon and oxygen are fused in sun-sized and larger stars. Silicon is only made in larger stars, which were exceptionally common early on. The following is conjecture, but based on our latest understanding of star formation. The first stars appeared when the universe was only a few 100 million years old. That is how long gravity took to work on primordial clouds and collapse them enough to trigger fusion. One star, forever beyond detection, found itself surrounded by a thin protoplanetary disk. With trace heavier elements, an object like Arikoth could have formed in the system's cold fringes, the first substantial body of rock and ices, the first solid object. While most astronomers do not consider Kuiper Belt objects proper planets, some are classified as minor or dwarf planets, and such a dwarf planet may have first formed before galaxies evolved. Though unlikely to host life, their formation depends on ices remaining solid far from parent star heat. But there is another kind of planet, much larger than any dwarf planet, that could have emerged early and might have supported life. These are Hycean worlds, coined by University of Cambridge researchers as a portmanteau of hydrogen and ocean. Currently hypothetical, astronomers have identified several candidates in Kepler and TESS surveys. Hycean planets are massive, approaching Neptune's size, but most bulk is thick hydrogen atmospheres. Those atmospheres can be thick enough to maintain pressure, allowing liquid water, perhaps as globe-spanning oceans. These planets may have formed extremely early. A small nugget of rock, enrobed in a water ocean, buried under a dense hydrogen atmosphere. But the oldest known planet is no super-Earth, mini-Neptune, hot Jupiter, Hycean world, or fragment. Its formal designation is PSRB 1620-26b, but most call it Methuselah, after the biblical character who lived the longest. Methuselah was discovered in 2003 by Stein Sigurdsson of Pennsylvania State University in globular cluster M4. Globular clusters are among the oldest star collections in the galaxy, believed remnants of cannibalized galaxies. Methuselah is a pulsar planet orbiting a dead core like the first known exoplanet. It is huge, over 2.6 Jupiter masses, orbiting at roughly Uranus's distance from the Sun. Its parent is not alone. There is also a white dwarf orbiting closer. While we cannot directly estimate Methuselah's age, we can determine its globular cluster's age, and stars in clusters appear roughly simultaneously. So with significant uncertainty, Methuselah holds the record as oldest known exoplanet, roughly 12.7 billion years old. Like all pulsar planets, astronomers are not sure how Methuselah formed. Given its bulk and regular distance, most believe it formed around a sun-like star in M4's outskirts almost 13 billion years ago. The star and its bulky planet migrated toward M4's center, where the planet witnessed drama unfold. Once stabilized, Methuselah's star aged normally, eventually becoming a red giant. Its swollen atmosphere spilled onto the neutron star, transferring energy and angular momentum, causing the neutron star to spin up into a pulsar, rotating 100 times per second. After Methuselah's original parent star exited the red giant stage, it became a white dwarf. After all this drama, Methuselah remained for billions of years. Methuselah is an unlikely candidate for life, at least as we understand it, like any gas giant. But material to make a planet can also make a moon, and a system does not need as much raw, heavy elements to fashion moons around a giant. If life found a home on a Methuselah moon, it would have been shielded by ice from cosmic dangers, supernova radiation, red giant heat. It could have persisted, even thrived. It may still be there, the oldest living creatures orbiting the oldest known planet, the end result of a genetic lineage going back to the dawn of stars and galaxies, retaining memory of a far different cosmos. If they had eyes and curious minds, they could have watched the entire Milky Way emerge and evolve. If they developed telescopes to peer deeper, they might train curiosity on a small, insignificant branch of a great spiral arm. In detailed observations, they might find a star not unlike the one that once hosted their system. They would find a gas giant smaller than theirs, but still mighty among its family. They would detect the thin atmosphere of a water-rich world, and in that atmosphere, the unmistakable sign of that planet's newcomer life, only recently arrived on the galactic scene. If you enjoyed this exploration of ancient worlds and cosmic possibilities, make sure to subscribe for more journeys across the universe. Give this video a like if you found it fascinating, and share it with anyone curious about where we come from and what might be out there. Your support helps bring more stories like this to light. Thank you for watching.